Hello everyone. Eh, Welcome to the mechanics of materials. And this video we are going to talk about the moment calculation in 3D space. And in the last video, I just show you the cross product and show you how if we have two vectors. Suppose we have two vectors, and what's the result if you're doing a cross product of the two vector. You can write it in condensed form. It's 3 by 3 determinant, and then yeah, 3 by 6 determinant. You just need to know the rule to expand this 3 by 3 determinant. Okay, okay. So let's go back to the moment. Okay, the moment, right? The moment is like in previous video I said in 3D in vector formulation, moment vector. Especially, we need to important point is that you need to know the reference point or reference axis. Okay, the moment with respect to axis is equal to r cross f. It's position vector cross your force vector. Okay, r cross f. So here's a graphic representation of r cross f. So you have position vector. For example, the right hand side in this picture is r is here, and you need the cross f, r cross f. Okay, r cross f. Okay, r is here, and then cross f is here, so it's r cross f. Okay, let's see. R cross F. Okay, here is R cross F. So R is here, F is here. So R cross F is R cross F. That's why he R cross F, R cross F, R cross F. Okay, R cross F. It's not R cross F. Why doesn't it go this way? You have to go this way. Yeah, maybe I'll think about this later. Okay, okay, never mind. Okay, maybe I just raised a lot of questions. Okay, just simply speaking, the moment is R cross F, doing the product between your position vector and your force vector. Okay, okay, so okay. And there is a very in this textbook it raised a concept called principle of transmissibility. Okay, this is just a property of force vector. Force vector is a sliding vector. For example, if I have force vector here and the r1 cross f, r2 cross f, r3 cross f. Okay, this force vector, this is one force vector, but we have three different position vector. But interestingly, these three position vector doing a cross product with this force vector, their answer will be all the same. Okay, their answer will be all the same. Okay, that's very interesting. But we can use a very simple way to prove this concept because no matter R1, R2, R3, their labor arm is all the same. Okay, their labor arm is all the same. Why? You just see the labor arm. Let's just pretend it's 2D case. But in fact, this will form more proof. But in this class, I'm not really interested in the proof because most of you don't like the proof. Okay, so this principle of transmissibility, I think we just use very simple way to prove that. Okay, because for the R1, labor arm is here. Okay, let's not look that very straight. Okay, R1 labor arm is here, and R2 vector, you will see that R2 vector, the labor arm seems to be here as well. Okay, the R3 vector, the labor arm is still here. Okay, so if we pretend it's a 2D case, okay, you will see R1, R2, R3, they have with respect to this force vector, they all have the same labor arm here. They all share the same labor arm. Okay, share the same labor arm. Okay, and since the force vector is the same, so the moment cross product will be the moment will be the same. Okay, R1 cross F, R2 cross F, R3 cross F. They will have produced the same moment vectors. Okay, and the next thing is oh sorry, of course okay, of course this proof has yeah, this is a very simple proof I just said. Okay, but there is formal proof of this principle of transmissibility. Okay, you can look up the where I give you the web link. Okay, you can go to the website to see the formal proof of the principle of transmissibility. Okay, yep, it just to show you the force sliding vector. Okay, that's all. Uh-huh. Okay, so the moment is a position vector cross the force vector. Okay, if we we express our vector are all Cartesian vectors, so R cross F will equal to this condensed form, the determinant of the 3 by 3 matrix. Okay, and the first row is the unit vector of x-axis, y-axis, and z-axis, yi, j, k. And the second row is the component of your position vector, and the third row is the component of your force vectors. Okay. And the moment is a vector. Moment is a vector. So we can calculate the resultant moment, just like we calculate the resultant force. Okay, because force is a vector, and they want to. And previously we showed lots of calculation on finding the resultant force. Okay, resultant force, and we do a similar calculation here because we sometimes in our system we have lots of moment acting on the system, so we can calculate a resultant moment. Okay, just like we did on resultant force. Okay. Okay, just sum of the moment vector together. Okay, that's very easy and vector calculation. I hope you can all understand this. Okay, so I don't have to address this more. Okay, so and then raise one example to let you practice the 3D moment calculation. Okay, and suppose there's a tractor here. Okay, here there's a cable here, a cable here, and the cable is the fixed point of this cable is on point A, and this tractor is pulling this cable. Okay, and the force of this pulling is about 2 kilonewton, 2 k newton. Then very simple question. You want to ask what is the moment caused by the force? What's the moment caused by the force? And express the result as a Cartesian vector. That just means you want to calculate your moment, okay? And express your moment as a Cartesian vector, okay? So in the moment calculation, okay, I just write a formula here. In a moment calculation, and in a moment calculation, all we need to know is moment is the r cross f, okay, and it all is a reference point. Okay, so we need the position vector and the force vectors. Okay, force vector, obviously force vector is here because this tractor is pulling through this direction. Okay, so the force vector is here. Okay, that's no problem. Force vector here, and it give you the force. It give you the force. Okay, we see the vector is a magnitude and times the direction, unit vector of force. And the magnitude, yeah, we know the magnitude. Give it the magnitude is 2k. Okay, so let's use kilonewton as the unit. So I just write it 2. Okay, but remember, it's this 2 means 2 kilonewton, and times the force and 10 unit vector of the force. So what the unit vector of the force, because in previous video we introduced a concept is called force along a line. Okay, this force right now is along the AB vector. This force right now is along the AB vector. So the direction of your force is equal to the direction of your AB vectors. Okay. So how to calculate the unit vector of AB? Okay, this is unit vector of AB. How to calculate the unit vector of AB? First of all, you need to know what's your AB vector. Okay, is so how to calculate the vector? Yeah, because calculate vector. And this problem, it gives you the coordinate. Okay, it gives you coordinate for some reason. Okay, you need to use this coordinate to find out the AB vector. Okay, AB, so it's A to B, so it's just the point B minus point A. Point B minus point A. Okay. So what's the coordinate of B? It's A to B. Be careful. It's A to B vector. So it's point B minus point A. Be careful. Okay, so AB. Okay, what's the position of B? Okay, I hope you can read the coordinate. Be careful. Okay, this x-axis is here, y-axis is here, z-axis is here. So x-axis, okay, x-axis. So here is 4. So it's 4. Y-axis here. So it's 12. And z, I think it's on ground, so z is 0. So what's the coordinate of a? X is 0, y is I think it's also 0, and z is 12. Okay, so the coordinate of a is 0, 0, 12, and coordinate of b is 4, 12, 0. Okay, so the AB vector, just subtract these two. Okay, so be careful, it's b subtract a or b subtract a, so it will become 4i plus 12j and minus 12k. Okay, because b minus a. Okay, once you got your AB vector, so you can calculate your unit vector of AB. And how to calculate unit vector? Don't forget, it's just component divided by your magnitude. Component divided by your magnitude. Component divided by your magnitude. Okay, I think I have to remove this. Not remove this to here. Okay. Okay, so how to calculate the unit vector of AB? Unit vector of AB, okay, it's component divided by the magnitude. So, okay, how to calculate the magnitude of vector? Don't forget it. Okay, magnitude of a vector is equal to square root of 4 square plus 12 square plus minus 12 square. Okay, so what's the result? Don't forget to use your calculator. It's very important to use calculator. You need to practice at your ordinary time. Okay, square roots 40. Let's take 17.44. Okay, so we have magnitude. So our unit vector of AB is equal to 4 divided by 70.44 I plus 12, 17.44, and the J, K minus 12, 17.44 K. Okay, so what's the result? Yeah, and do the count. 4 divided by 17.44 or 0229. Is this correct? 0. Let's say, okay, we'll take a 3-digit I plus 12 divided by 7.244. 0.68 J minus oh, sorry, 12 divided by okay, 0.688 K. Okay, so this is your unit vector of AB, and unit vector of AB equal unit vector of F. So finally you got your force vector is 2 kilonewton times this. Okay, this is the force vector. Yeah, I think it's just here, right? The answer is here. Okay, so I don't want, so that's why just the answer is here. Okay, finally, okay, so this is the force vector. Okay, we got our force vector. Okay. Okay, so next one is where is our position vector? R cross F, and with respect to O is here. Okay, the fourth vector is here. So how to choose the position vector? And we want to calculate the moment with respect to the position of the origin. Okay, so the obvious choice, your position vector is this one. Obvious choice is this one. This is obvious choice. Obvious choice is this one. This is your force. This is your position vector. This is a position vector. Oh, here is your position vector. Okay, because force vector is here, and we want to calculate the moment with respect to this origin point. So the most easy choice, the most obvious choice, the position vector is this one. It's OA vectors. It's OA vector. Okay, and OA vector is 0i plus 0j plus 12k. Because this O is origin, so it's very easy to write down the position vector of OA position vector. Okay, and in this problem, you can also choose another position vector. The other position vector is hard to see. Okay, because like we said in previous slide, we just say the force is a sliding vector. Force is sliding vector, and we want to calculate the moment with respect to O. There, you can choose this vector. Okay, you can choose the OB vector as well. Okay, you can choose the OB vector as well. Okay. And if you do the OA vector cross F and OB vector cross F cross the force vector, the answer will be the same. But in this, you can try yourself. If you can try to use the OB vector, do a cross product, cross the F, and see if the answer is the same. Yeah, in here I just use this one because OA is obvious, very obvious to see. Okay, it's a very obvious choice. Okay, so let's calculate the moment with respect to O is equal to ROA cross force vector. Okay, so we use the 3×3 determinant JK. So the first we'll write a component of position vector. And the third row, we have to write down the force vector. So 4,588, 1.376 and minus 1.376. Okay, so this is a 3×3 determinant. I'm sorry about this. This is not. This doesn't align very well. Okay, yeah, but I don't want to change it. Okay, so what is our result? Okay, so I have to erase this part. Okay, if you want to look at this part, just rewind. Okay, just rewind. Okay, I need more space. This problem. Okay, so let's start with the 3×3 determinant calculation. So we use these three elements as a cofactor and do the expansion. First is I, so it will be 0, 0, 0.4588, 1.376 is J, and minus J. Don't forget the plus, minus, plus, and minus J. And we block this element, and I is block these two elements. Sorry. Yeah, I make a mistake. Okay, let's try it. So if doing the first cofactor, so it's here, you block this element, so it will be 0, 1.376, and 12 minus 1.376. Okay, so you use I doing the cofactor expansion, and if you use the J doing the cofactor expansion, you just block this element, so it's 0, 12, 0.4588, and minus 1.376. Okay, and the final one is the K. Okay, K, let's see. K, if you block these two, and that element will be 0, 0, Yeah, 0.4588, 1.376. Okay, so okay, the 2 by 2 determinant, I think it's very easy. 2 by 2 determinant. Let's see the result. Okay, doing this product minus. Okay, so it will be um 12 times 1.376, but it's minus, so it's minus 16.51i. And I think that doing this product, okay, so it's minus, so it will be a j, so 12 times 0.4588, so it will be 5.5 1j, and final one is 0. So I think this is the result. Your moment is equal to minus 16.51i plus 5.51j. Did I do the right calculation? Let me check the answer. Check the answer. Yes. Yes. Okay, the answer is correct. So this example is for very simple example to help you to practice the moment calculation in 3D space. And yeah, the most important thing is to find the position vector. Yeah, finding position vector, I think the most important part is 3D moment calculation. The force vector, not really, because the force is easy to identify. Force vector easy to identify. The position vector is not that easy to identify. Okay, I just stop video here. See you in another video. Bye bye.